This week's second learning goal is that students will be able to interpret the phenotype pedigrees to identify the genotypes of individuals and the type of inheritance. You can see right here I have given you 4 different pedigrees that you will need to know. So let's talk about pedigrees. When we're talking about patterns of inheritance, these are patterns that we see in how specific traits are passed from one generation to the next generation. This is actually a really important thing to study when we're looking for causes of disease, causes of disorders. Scientists spend a lot of time. Matter of fact, prior to me coming back to teaching, I spent 4 years working in genetics, searching the human genome for causes of inherited eye disease. And so I spent a lot of time looking and putting together pedigrees, trying to identify how these disorders were passed down through generations. This is actually a really important thing for us to know because it helps us to understand what's the probability that we could have children with certain disorders. And so patterns of inheritance and pedigrees are very helpful. A pedigree is just simply a chart or a tool, a diagram that shows how a trait is inherited over several generations. You can see in our picture here that this is a pedigree, and in this pedigree there are 1, 2, 3, 4 generations of individuals. And so genetic disorders are diseases or disabling conditions that have a genetic cause, or they're found in our DNA. So the inherited pattern of a genetic disorder can be identified using one of these pedigree diagrams. And so a few things that you have to know about pedigrees. They're universal, so we don't just get to make up what we want each shape to be. The shapes come with a very specific universal key. And so what you need to know are a few of those things. You first need to know that a male on a pedigree is going to be represented as a square, and a female on a pedigree is going to be represented as a circle. If the individual is affected, meaning they express the phenotype of the disease or the disorder or whatever the trait is that we're looking at, that means that they will be shaded completely in. So the affected individual will be completely shaded in, while the unaffected individual will not be shaded in. And so all of the black circles and black squares, those are affected individuals. So those should jump out right away. The ones that are not shaded in, those are not affected. So we're going to start looking right up here at this top generation. So generation number 1. Generation number 1, you see the male and the female, and you can see the line that is directly across from them. Okay. So this line right here, that's going between the square and the circle, that line is going to indicate mating. And so those two individuals have offspring. The offspring then will come down from that connected line, and then they'll branch out. So they have one son, they have a daughter, they have another daughter, and another son. And so this generation 1, they had 5 children. They had 3 daughters, 2 of which were affected, and they had 2 sons, 1 of which were affected. And the mother, generation number 1, was also affected. Now, only 1 of their 5 children have actually had children of their own, and this individual right here, had children with this offspring, or this male, and they produced 4 children. They produced 2 females, 1 affected, and they produced 2 males, 1 affected, of which though one of their affected females had children, and one of their affected males had children. And so that's how a pedigree works. It's really pretty simple and straightforward. In the event, this is not going to be on your assessment, but if you happen to have identical twins or non-identical twins would be written using the triangle here. Okay, so what can we do with these pedigrees? Well, we can come up with a pedigree based on studying the family. And then we can determine, well, here's this disease, here's how it's spread throughout the family, so what is its inheritance pattern? And there are mainly three that we're going to look at, inheritance patterns. Here's an example of one of them. So hemophilia. In royal families, hemophilia is very common. It is a recessive trait. However, there's something also pretty unique about it. It's not just a recessive trait. If you look at this pedigree, what is one of the first things you notice about the affected individuals? All of them are male. And so when I look at a pedigree and I see that it is 100% male affected, that's telling me this has to be sex-linked. This is somehow linked to the X or the Y chromosome. Now, your first thought might be the Y chromosome. However, if you take a closer look, you also are going to notice that there is no affected male who passes it on to an affected and has an affected son. And so no father passes this disorder, hemophilia, on to his son. I know there's a couple unique things here. For example, here I have just she has all of these kids. So we have offspring coming off of this female. What that means is that we don't know the male contribution of the genetics for these individuals. So for whatever reason, we have no idea of who that male is or what their genetics would be, and so we can't put them onto a pedigree such as this. And so the pattern of inheritance for this particular family or for this particular disease, which is hemophilia, would be known as sex-linked, and it is also going to be recessive. Now, how do I know it's sex-linked? Because it's only in males. I also know that it is sex-linked and X-linked in particular because no affected male passes it on to his sons, because a male passes the Y on to the son. And so, therefore, I also know it has to be recessive because here I have a generation, and these guys are unaffected, and they have a son who is affected. Now, if an unaffected couple has an affected child, the only way that can happen is if one of those unaffected adults is a carrier, and carriers only happen when they're carrying a recessive allele that needs another recessive allele in order to be expressed. A dominant disorder cannot have a carrier because if you have the dominant allele, if you're carrying it, then you also have the disorder. And so hemophilia is a sex-linked recessive trait. Excuse me. Let's take a look at this pedigree right here. So in this pedigree, what are some things that you notice right away? So we're looking for pattern of inheritance. Okay, is the pattern of inheritance, is it going to be recessive? Is it dominant? Or is it sex-linked? So those are the three that we're going to look for. If we look at this first pedigree, there are 4 generations, and this trait, this disease, does not show up until the 4th generation. In the 4th generation, now take a look at this. This is another unique situation because this is a double line. Does that mean that they got married and they got divorced and they got married again? No. What that means, and I know those of us living in the United States, this often bothers us. However, in other cultures, this is commonly practiced. These two individuals are actually cousins, and they had children. Now, in families, in royal families, for example, but in a lot of families that, in other countries, that actually practice what's called contiguity, and that is keeping royal blood within royal blood. They might not be marrying first cousins like in this pedigree. This could be, might not even be humans, but there is a much higher chance of that recessive allele popping up as a homozygous recessive. So in this situation, these two are cousins. So they had 3 children, and 2 of the 3 children are affected. When you have unaffected parents have affected children, you know automatically this has to be recessive. This has to be a recessive trait. Because, for example, generation 3, so generation person 3, 4, so this person right here is crossed with 3, 5, this person right here. Both of those individuals had to be heterozygous, and when they crossed, that little recessive allele came together in 2 of their 3 cases and produced a recessive trait. So that is a recessive pattern of inheritance. The next one here is dominant. If we take a look at this dominant pattern of inheritance, how do I know it's dominant? Well, I know it's dominant. The first key thing that I see is that there are affected individuals in every generation. And so if I have affected individuals in every generation, males and females both alike being affected, then that is a very high probability that this would be a dominant disorder. And so on the quiz, I'm going to give you some of these pedigrees, and I'm going to ask you, is it dominant? Is it recessive? Is it sex-linked? And so the last one that we'll look at again is the sex-linked. Colorblindness is sex-linked. In this one, this would probably be a little bit tricky because this could almost pass on as a dominant trait, because you could look at this and identify that, well, it's in every generation. And so this one we probably would want to know a little bit more information about the individuals. This is also a really tricky thing because you have an affected male with an affected male. This father did not give his son this disorder because this is, colorblindness is an X-linked disorder. And so this mother right here happens to also be big C, little c. She happens to be a carrier, and so her boys have a 50% chance. What do you know about generation 2, individual 10 and individual 12? Well, if the father is affected, then all of his daughters will be carriers. And so this one's a little bit